Hello and welcome to a new problem solving session. Here is a problem where we need to find a equivalent spring constant. Equivalent spring constant, that means we have got a system of springs and we need to find an equivalent that all the springs of the system needs to be replaced by a single spring. So let's look at the problem first. There is the problem saying find the equivalent spring constant of the spring system shown in the figure. So we can see the figure here, and the ladder on which the springs rest is infinite. That means this set of thing is infinite. Okay. And each of the platforms except the top one rests on two springs. The first one rests on three springs, and rest of them, rest of the platforms, they rest on two springs only, as you can see here. The spring constants of all springs are the same and equal to k. So spring constant is k, very quite common value. The axis of all springs are vertical. Okay. The mass of the springs and the platform can be neglected. This is the problem. So how can we solve it? Let's invite a force on the upper platform and call it F. And after you introduce the force F on the upper platform, there will be forces on other platforms as well. Let's call them F1, F2, F3, and like this. And also assume that under the action of this force F applied on the upper platform, the displacement of the platform is delta x. The first platform, its displacement is delta x. Just say delta x, so that this platform we would like to write delta x1, another one delta x2, and another one as delta x3, and so on. Then from the condition of equilibrium of the upper platform, that means the sum of the forces acting on it is equal to 0, we can find the equivalent spring. Let the equivalent spring is K equivalent. Let's call this equivalent spring constant. Then you can see here its value can be written simply by F upon delta x. And what is the value of F? Because we don't know, because we have applied this force to start the solution of the problem. So we need to explore it a bit more. You can see here, this force F is basically, if you can see, the uppermost platform, that the forces you want to show on this upper platform, first force will be the F that is applied by some external agent. And then there are two kinds of springs, one of this kind and one of this kind. This spring is supported by a rigid platform beneath them. So this spring, this middle spring, can only be compressed by a length delta x, whereas this or this spring, left extreme left or extreme right springs, they will not be exactly compressed by an amount of delta x. This right spring, you can see here, it is getting compressed by an amount delta x from upward, and after that it compresses a length delta x1 to the spring just beneath it. That means to the platform just beneath it by a length delta x1. So the net compression on it is delta x minus delta x1. I am guessing delta x is greater than delta x1 because forces are getting diminished as we move from up to down. So this thing is compressed delta x from upward, and delta x minus delta x1 is the net compression produced in this spring, because its lower end gets by an amount of delta x1 lower. So the net compression produced in these two springs, left and extreme right, is delta x minus delta x1. So there are two forces acting on this upper platform. One by this spring, the middle one, and that will be simply k delta x, because the spring constant is k. And next there will be one more force that will be applied by both these springs, the left and right spring, and they get added. So we can write here this force will be 2k delta x minus delta x1. So this first expression, that is k equivalent, you can write here, this is f by delta x, and f can be easily replaced by k delta x plus 2k delta x minus delta x1. And to complete the statement, I can divide it by delta x. So this is one statement here, and this comes from, since this platform is at rest and it is massless. The main reason writing this equation, f equals k delta x plus 2k delta x minus x1, is that this platform is massless, negligible mass. Later we can simplify this expression, and we can write here 3k minus 2k delta x1 by delta x. And again we can simplify something. If we take k out, we can write it, this will be equal to 3 minus 2 delta x1 by delta x. So this is basically the value of k equivalent. And to find the value of k equivalent, we need to find out the value of delta x1 by delta x. And how can we do this? To do so, we need to write down the equilibrium conditions of the platforms in our next statements. So let's prepare it. we can simply write here that what can be the value of f1. And I know f1 was acted upon by this spring on this platform, so f1 is here, and its displacement is delta x1, and this platform displacement was assumed delta x2 and this one as delta x3. So again, if I can make the free body diagram for this platform, the force F1 comes from upward, and you know F1 is exerted by this spring, and this spring is only compressed by a length delta x minus delta x1. This spring, the compression in this spring is delta x, because delta x is the compression of this upper platform, so that this spring is compressed by a length delta x minus x1. So f1 we can write simply as delta x minus k delta x minus delta x1. We can write it in this manner, and we can also write f1 by considering its free body diagram. F1 acts from upward, and k delta x2 is exerted by this spring. K delta x1 is exerted by this spring, and this spring you can say is again compressed by an amount delta x1 minus delta x2. That is why another force act on this platform, and that is equal to k delta x1 minus delta x2. So we can write here f1 equals k delta x minus delta x1, or f can be written as k delta x1 plus k delta x1 minus delta x2. K delta x1 plus k delta x1 minus delta x2. And in the similar manner, if you want to write f2, you can write here, this will be k delta x1 minus delta x2, or it can be written as k delta x2 plus k delta x2 minus delta x3. You can see that and verify by yourself. And in the similar manner, f3 can be written as k delta x2 minus delta x3, and that will be equal to k delta x3 plus k delta x3 minus delta x4, which is not shown here. And there will be many more equations like this, because they are infinite in number. The ladder has infinite legs. So if you can add all of them, especially if we consider this part of the equation, and if we can add these equations together, we can see k is gone from the equations, and left hand side is simply like left hand side delta x1 delta x1 delta x2 delta and delta x3 will be cancelled by the next equation. So left hand side of the equation is simply delta x, and right hand side you can write here this thing cancelled out, this thing cancelled out, so this thing will be cancelled out next, and we can write the left hand side of the equation simply. K is already cancelled, so we can write here something like 2 delta x1 from the first equation, that is 2 delta x1 plus delta x2 delta x3 and so on. This is our equation 1. If I can write like this, this is our equation 1. And you can also see one thing. This spring constant of this spring, this spring, this is every spring, the spring constant of every spring is constant. So it is, since it is compressed only by delta x, by an amount of delta x1, it's a spring constant. You can write f1 by delta x1. This is spring f1 by delta x1, and this spring constant you can write here f2, similar manner f2 by delta x2, and this spring constant like f3 by delta x3, and all are same. So you can write another equation here, that we have f1 by delta x1 equal to f2 by delta x2 equal to f3 by delta x3 equal to many more. And for f1, f2 and f3, we can, if we can write these equations, we can write it something like f1 equals k delta x minus delta x1, and that is divided by delta x1. f2 in the similar manner by k delta x1 minus delta x2 by delta x2, and similar manner f3 can be written as k delta x2 minus delta x3 by delta x3, and like this. So what can we get from this equation, this set of equation? You can see what can we get. K is getting cancelled out. So the first thing is delta x by delta x1 minus 1, and minus 1 equal to next, in the next step we are getting again delta x1 by delta x2 minus 1. Again in the next step you can see here delta x2 by delta x3 minus 1 equal to this. We can write something like that. And we can write this equation as simply as sorry, this was x1. So we can simply write this equation as delta x by delta x1 equal to delta x1 by delta x2 equal to delta x2 by delta x3, and this is simply can be written as, simply we can, if there are n number of such springs, we can simply write it equal to n. Of course this is n is greater than 1. We don't know the exact value, but we can simply write it here n. And so we are going to form the equations. We can write here delta x1 equal to delta x by n, and in the similar manner delta x2 equal to delta x1 by n, that is equal to delta x upon n square, and in the similar manner we can write delta x3 equal to delta x by n cube, and so on. So that we already have an equation where delta x was equal to 2 delta x1, 2 delta x1 plus delta x2 plus delta x3, like this. So we can use that equation here, and we can write here delta x equal to 2 delta x1, 2 delta x1, that was 2 delta x1 plus delta x2 plus delta x3 plus delta x4, and like this. And if we put this set of equations into this equation, we can write here delta x equals twice delta x by n plus delta x by n square plus delta x by n cube plus delta x by n raised to 4, and plus like this. And then we can see that it's a condition of geometric progression, and if we cancel all these delta x's, we can write here something like 1 equals 2 by n plus 1 by n square plus 1 by n cube, and like this. So that we can write here can I take this n to the left side, so that we can write here n equals 2 plus 1 by n plus 1 by n square plus 1 by n cube, like this. I can write this, and then again I would like to write 1 plus 1 plus 1 by n plus 1 by n square plus 1 by cube, and like this, so that we can get a terms of geometric progression. And in the next step we can write here it as 1 plus, and I can sum this a by 1 minus r, and r is simply 1 by n, so we can write here n equals 1 upon 1 minus 1 by n, and it becomes 1 plus n by n minus 1, and that is equal to 2n minus 1 by n minus 1. So we have an equation, and that is all equal to n equals 2n minus 1 by n minus 1, so that I can write here in the next step n into n minus 1 equals 2n minus 1, and I can make an equation something like n square minus 3n plus 1 equal to 0, so that we get the value of n, and that will be equal to 3 plus minus under root 5 by 2. But I'm going to accept only positive value, positive sign of this solution, positive root of this solution, because we know n is greater than 1, so that I can write here n equals 3 plus root 5 by 2, and you can see here that this n is equal to delta x by x1. We were looking for to solve this problem. Finally, to solve this problem, delta x by x1, delta x1 by x, okay, delta x1 by x, but we got something delta x by n. We get, after getting n, we got delta x by delta x1. So our k equivalent can be written as k 3 minus 2 delta x1 by delta x. It is, and this becomes k3 minus 2. We can reverse it, 2 by 3 plus root 5, and that will be equal to k 5 plus 3 root 5 divided by 3 plus root 5, and this, after calculating it, you can get here k root 5, and this will be the final solution. So thank you very much for watching.